In today's lesson, we're going to look at rational functions and how to algebraically determine where holes and asymptotes exist. So our essential question is, how do I algebraically determine the discontinuity and end behavior of a rational function? Because discontinuity is going to be determined by your holes and your asymptotes, or your vertical asymptotes, and your horizontal asymptotes would affect the end behavior of a rational function. So let's begin by defining a rational function. So a rational function, f of x, is the quotient of two polynomial functions, a and x and b and x, where b is non-zero. Because if b were equal to 0, then we would have an issue with our domain. This whole function would be undefined because you cannot divide by 0. One of the simplest rational functions is the reciprocal function, which is graphed here. You'll notice that this has a break in the domain at x equals 0. This red line represents a vertical asymptote. You'll also notice that the same function is approaching the line y equals 0 on its end behavior. This red dotted line is representing a horizontal asymptote. So the tips on your screen show you how to algebraically find any holes and vertical asymptotes that may exist. Since there are going to be polynomials in the numerator and denominator, you're going to begin by factoring the top and bottom. You'll cancel out any common factors, but these ones that you cancel are going to give you the location of the holes. Anything that remains in the denominator, you're going to set it equal to 0, and this is going to give you the equations of any vertical asymptotes where there is infinite discontinuity. I always say, remember, holes divide out, asymptotes don't. Horizontal asymptotes are determined by the degree. So if you have a polynomial function where the top degree is greater than the bottom, like something like x cubed over x minus 1, this top degree is bigger, there's not going to be a horizontal asymptote. Where if the top degree is equal to the bottom degree, for instance, let's say you have x squared over x squared plus 7. These are equal. Let's actually make this a little fancier. Let's say 4x squared plus 7. Because my degrees are equal in the top and bottom, there is a horizontal asymptote. And where is it? Well, it is the quotient of your leading coefficients. So there would be a horizontal asymptote here at y equals 1/4 in my first kind of scenario. Third scenario is if the top degree is less than the bottom degree. So that would be where you have x over x squared plus 1. Okay, so the bigger one is on the bottom. This is always going to have a horizontal asymptote at y equals 0. So of course, let's illustrate this with some examples. So this first one says to find any holes and the equations of any vertical and horizontal asymptotes. This rational function is already factored for you. So the first thing I notice is that I have two factors, the 2x minus 5, they're going to cancel. 2x minus 5 and 2x minus 5. But I recognize that this is going to produce a hole. So if I just take this 2x minus 5, set it equal to 0, gives me 2x equals 5, and x equals 5 halves, I have a hole at 5 halves at some y value. I'm not going to focus on the y value at the moment. And this equation then simplified to 7x over x plus 7. Let's talk about any vertical asymptotes. So a vertical asymptote comes from our denominator. It's anything that's going to break your domain. And since x plus 7 equals 0 would cause our domain to be 0, x could not be negative 7. So x equals negative 7 is the equation of our vertical asymptote. And then as far as a horizontal asymptote, well, we have to compare our degrees. So our degree in the top and the bottom, they're equal. When the degrees are equal, it is the ratio of our leading coefficients. So that would be 7 over 1. I'm going to have a horizontal asymptote, so it's a horizontal line in the form of y equals, and it would be y equals 7. We'll pull this all together by looking at the graphs shortly, but let's do one more algebraically. So this particular example is not factored, so my suggestion is begin by factoring your top and your bottom. So this would produce, let's see, you can factor out a GCF of 3 times the quantity of x plus 3. The denominator is quadratic, so I'm going to try factoring this into, I'm going to try 3x minus 7 and x plus 3, because negative 7 times positive 3 would give me negative 21. Product of my first, 3x times x would be 3x squared. Outer would be positive 9x. Inner would be negative 7x. That adds to 2x. So I have it factored correctly. Remember, off on the side, you can do the tic-tac-toe method just to factor a quadratic if necessary. Okay, so what do I see here? My x plus 3 and x plus 3 will cancel, but immediately I'm going to recognize that that would produce a hole or removable discontinuity. So this would be x plus 3 equals 0, and that means I have a hole at negative 3. So it's going to be, there's some point, negative 3 with a y value. That would be a hole. Now, as far as vertical asymptotes, they come from the denominator of my simplified h of x, which would be 3 over 3x minus 7. And my vertical asymptote would be anything that breaks my domain. So 3x minus 7 equals 0. If I take that denominator, add 7, divide by 3, I have a vertical asymptote at x equals 7/3. So that's where I have infinite discontinuity. And then my horizontal asymptote, let's see if I have one. Well, let's compare our degrees. So the degree in the denominator is larger, so I do have a horizontal asymptote. This is the case where it's y equals 0, so your end behavior would approach 0 on either side. In this next example, we're going to thoroughly examine this function. We're told to determine any vertical or horizontal asymptotes, holes, and intercepts, sketch the graph, and state the domain, continuity, and end behavior. So pause the video and begin by factoring the numerator and denominator. So mine factors into what you see on your screen. I'm going to cancel my x minus 3's, and I get f of x is equal to 8x over 2x plus 1. So what does this tell me? Well, I'm going to begin with the hole I see, and that would occur at 3 based on the factors I canceled. Now, if you actually wanted to find the y value, what you do is you plug it into this simplified version. If so, f of 3 would be 8 times 3 is 24 over 7. It would be 24/7. Check with your facilitator. He or she may be satisfied with you just finding the x value of the hole. Okay, how about any vertical asymptotes? Well, that comes from the denominator of my simplified version. So I have 2x plus 1 equals 0 would break my domain. So subtract 1 and divide by 2 would be x equals negative 1/2 for my vertical asymptote. So I'm going to go over to my sketch, and I'm going to draw in a vertical asymptote at x equals negative 1/2. How about horizontal asymptotes? Well, the degree of the top and bottom are equal, so it would be formed by the ratio of 8 over 2. So y equals positive 4 would be my horizontal asymptote. So I'm going to draw a blue line, dotted line here at y equals 4. And next I need to find any intercepts, and then I'll state domain continuity, etc. So my y-intercept, of course, is obtained by plugging in 0 for x. So f of 0, if I plug that in, I get 0 in the numerator. So my y-intercept is at 0, 0. It's going to cross at the origin. An x-intercept is found when you let y be 0. So if I let y be 0, I would get 0 equals 8x over 2x plus 1. I'd multiply both sides by 2x plus 1, and I would just get 8x equals 0. So really, your x-intercepts just come from your numerator. So in the future, I'm just going to say my x-intercept would be 8x equals 0, and then that gives me x equals 0. So I see that my x-intercept is 0, 0, which really we kind of already knew here because the y-intercept, the origin, is both an x and a y-intercept. So I'm going to put a point at the origin because I know it crosses there. I need to state my domain, continuity, and behavior. So my domain, well, I already have my asymptotes and my holes. So otherwise it would be continuous everywhere else because it's polynomial. So it would be negative infinity to negative 1/2, which is where my vertical asymptote is, union, negative 1/2 to, and then I have a hole at 3, union 3 to infinity. And you may prefer to do it after your sketch to state your domain. My continuity, I'm just going to go back and kind of add this in. So we stated that I had a hole, so that would be removable discontinuity at x equals 3. And then where my vertical asymptote is, that would be infinite, oops, just spelled that wrong, infinite discontinuity at the vertical asymptote of x equals negative 1/2. The two things I have remaining are to state my end behavior, and then I need to sketch this. So my end behavior would be affected by my horizontal asymptote, so the limit of f of x as x approaches negative infinity is equal to the horizontal asymptote, which is 4. And then it would be the same on the right. Now, without even looking at my graphing calculator, I kind of know what's kind of happening here. I'm going to 1, 2, 3. I know I have that hole at 3 and 24/7, so it's going to do this, and then it's going to approach that horizontal asymptote, and then it's going to be up here like this. Again, not crossing over vertical asymptotes. Just something that's kind of interesting is functions never cross over vertical asymptotes. Now, technically, they can at times cross over horizontal ones, but they do approach them as they get, as x increases or decreases. So I've just graphed the function in Desmos to see how we did. I think you can see that it looks pretty good. We definitely have a horizontal asymptote at 4. We have one here at negative 1/2. Crosses x and y axis at the origin. You cannot see the hole readily unless, let's see if we can get it to go right on 3. Sometimes it's tricky with Desmos. There we go. You can see it says 3. It's undefined because there is a hole right there. The y value is undefined in the original function, but we did discover that the actual location of the hole was at 3, 24/7. All right, so we've got it. Let's do one more example here. G of x is equal to x plus 1 over x squared minus 9. So we are going to factor this to see if we have any holes where there would be removable discontinuity. So I see the difference of two squares pattern in the denominator. So looks as if there are no holes, right? So how about vertical asymptotes? Definitely. In the denominator, we have vertical asymptotes, which means we would have infinite discontinuity. So I'm going to state that right away, infinite discontinuity at our vertical asymptotes, which would be x equals -3 from the first and x equals +3. So immediately I'm going to go over to my graph and I'm going to sketch my vertical asymptotes. Okay. Moving on to any possible horizontal asymptotes. Well, the degree in the denominator is greater, so we do have a horizontal asymptote, and this is the scenario where it's at y equals 0. So it's on top of the x-axis. How about our intercepts? So the y-intercept is, of course, when we do g of 0. So if I plug in 0, I would get -1/9. So I'm just going to estimate where that is. It's going to be really close to the origin, closer than where I have it, but easier for the eyes to see if I'm a little bit inaccurate. My x-intercept, again, comes from the numerator set equal to 0. So if I do x plus 1 equals 0, I get x equals -1. So the x-intercept is -1, 0. So that is right here. So next, I'm going to state my domain. And my domain is broken by the vertical asymptote, so it's from -infinity to -3, union -3 to +3, and then 3 to infinity. I also need to state my end behavior, and I know that it will approach 0 on either side because it approaches that horizontal asymptote. So the only thing I have left to do is sketch, and I can't quite tell exactly what the shape looks like, if it's going to be like this, kind of like cubic in the center. So one way to do it is to test values as it gets closer by plugging it into your function. That would be completely algebraic, but it would be acceptable to toss it in the graphing calculator and get a sense of what the rest of the graph looks like. And when I do that, I can see that the graph looks like this, and it's approaching, of course, those vertical asymptotes. It never gets vertical despite my poor sketch, and then it approaches my horizontal asymptote, and then it switches to positive range values over here. So that is a pretty cool looking function. So it's time for you to practice. Please reach out if you have any questions.